Editor Sam here. Unfortunately, I have to re-record the voiceover for the entire lesson because OBS did not store my original audio recording correctly. So the goal for this lesson is to discuss two vectors that are associated with a parameterized curve called the unit tangent vector and the unit normal vector. We'll talk about what the formulas are for those vectors, and we will talk about what they mean and what they're telling you about the curve and about movement along that curve in space. So to begin with, let's go ahead and define the unit tangent vector. The unit tangent vector has the notation capital T function of lowercase t, where the capital T stands for tangent and the lowercase t is our parameter, typically representing time. And the formula for the unit tangent vector is exactly what it should be based on the name of this vector. First of all, tangent vector, remembering from the previous lesson, the tangent vector to a parameterized curve is given by its velocity, the result of the first derivative, r prime of t. Now, if we want to take that tangent vector and turn it into a unit vector, a vector of length 1, then we would also do that in the typical way. We would calculate the length of the tangent vector, the length of r prime, and then we would divide the tangent vector by its length to turn it into a vector of length 1. Now let's go ahead and summarize some of the important properties of this unit tangent vector, capital T. Once again, the name of this object is very self-explanatory. The first important property of this vector is that it is a unit vector, and it has a length of 1 unit at all times. The second important property of the unit tangent vector is again in the name. It is tangent to the curve and to the path of motion at every given moment. Now let's go ahead and do a quick example of actually calculating the unit tangent vector to a parameterized curve. And here we have the parameterized curve, two-dimensional. The first entry is t, and the second entry is t squared. So to begin with, we're just going to go ahead and find the first derivative of this vector valued function using the usual component-wise method. So r prime of t in this case is for the first entry 1 from the derivative of t, and in the second entry 2t from the derivative of t squared. Now let's go ahead and find the length of this vector valued function using the standard length formula and process. We'll go ahead and take the square root of the first component squared plus the second component squared, which after simplification becomes the square root of 1 plus 4t squared. So then to find the unit tangent vector, all we have to do is take t prime, the ordinary tangent vector, and divide out that length. So we'll do that division component-wise, giving us 1 over the square root of 1 plus 4t squared, and then 2t over the square root of 1 plus 4t squared. Here on GeoGebra, I've created a visual representation of this problem. In blue, we have a parabola, and that is the parameterized curve corresponding to this r of t function that we were given in this problem. You have the tangent vector to the curve, or in other words, the velocity vector, r prime. And we can see that it's tangent to the curve, and it also has a fairly considerable length. In this image, it looks like it's about 4 or 5 units long. We also see that if you extend that tangent vector infinitely in both directions, you get the tangent line to the parameterized curve, which we discussed in the previous lesson. So where is the unit tangent vector in all of this? We can see that the unit tangent vector points in exact same direction as the regular tangent vector. The only difference is that the unit tangent vector is much shorter and has a length of exactly 1 unit. And this is true no matter what time you're talking about, no matter what position you have along the parameterized curve, the unit tangent vector points in the same direction as the velocity. It's just been rescaled so that it always has a length of 1. So a quick remark in terms of what the unit tangent vector is actually saying to us about the curve and motion along this path. Let's remember that the tangent vector, or in other words, the velocity vector, contains two pieces of data about the object's movement. It contains information about the direction of the object's movement, and it also contains information about the speed at which the object is moving. The unit tangent vector is essentially a way to take that mixture of those two pieces of information and separate it out. One separate quantity that tells you about the object's speed and another separate quantity that tells you the direction of the object's movement. The unit tangent vector, because it comes from taking the velocity vector and dividing out the speed. Basically, the unit tangent vector communicates only the object's direction of movement. And then you can separately talk about the speed of the object by looking at the length of the velocity vector. Now let's talk about the unit normal vector to a parameterized curve. And the notation for the unit normal vector is just a capital N as a function of t. Here the capital N stands for normal. Now the unit normal vector is defined by the following formula. You start by taking the derivative of the unit tangent vector that we just talked about, take the derivative of capital T, and then once again divide out the length of that t prime vector. Divide it out so that n is a unit vector, as the name suggests. So just as a heads up, even though the unit normal vector is defined by this formula, we will never be using this formula to actually calculate the unit normal vector for a given parameterized curve. This formula is fairly difficult to actually use for calculations. So what we're going to do today is we're going to take this formula and we're going to use it just to understand the properties of the unit normal vector and how the unit normal vector appears on the graph of a parameterized curve. When it comes to actually calculating the unit normal vector, we will see a better formula in the next lesson that will allow us to calculate n a lot more easily. So now let's discuss some of the properties of the unit normal vector. And the first property is in the name itself. Of course, the unit normal vector by design is always a unit vector. At all moments of time, it has a length of exactly 1 unit. The second important property of the unit normal vector is that the unit normal vector always points in the direction that your object is turning at that moment. So if your object is turning toward the positive y direction, for example, your unit normal vector will be pointing in the positive y direction. So if, for example, I just draw some random curve oriented, roughly speaking, from left to right, and I mark a certain point on this curve at random. Let me just call it point A. If I wanted on this graph to draw the unit tangent vector, then I would draw that vector tangent to the curve pointing in the direction of motion, 1 unit in length. And if I wanted to draw the normal vector at that same location, I would observe that at that moment, I see that the curve is beginning to bend downward in the negative y direction. So I would draw my unit normal vector pointing in the negative y direction to reflect that, pointing the unit normal vector in the direction that the object is turning at that moment. Now you may have noticed that I have drawn the unit normal vector perfectly perpendicular to t at a right angle to the unit tangent vector. And that is a property of the unit normal vector, that n is always perpendicular to t, and we will explore that and we will prove that later on in this video. let me go ahead and find the tangent vector and the normal vector at another location along this curve for another example. If I mark a point B along that curve, I can draw the unit tangent vector by drawing a tangent vector of length 1 pointing in the direction that the object is moving at that moment. So that would be the unit tangent vector at the point B along this curve. If I wanted to draw the unit normal vector at that same location, I would observe that at that instant, the curve is beginning to bend toward the positive y direction. So I would go ahead and draw the normal vector in the positive y direction, perpendicular to the unit tangent vector at that instant. Let me once again demonstrate this situation on GeoGebra. So returning to that parabolic parameterized curve from earlier, now I have configured the picture to display the unit tangent vector to the curve and the unit normal vector to the curve at any given moment. And what we can see is that the unit normal vector is pointing in the direction the object is turning. For example, here we see the object / the curve is beginning to bend toward the positive x direction. So that's where the normal points. And as we change the instant in time and the point along the curve that is active, we can see that unit tangent vector and that unit normal vector adjusting. In this part of the video, we're going to give an explanation / a proof of why the unit normal vector has these special properties. First of all, why does it always point in the direction that the object is turning? And why is it always exactly perpendicular to the unit tangent vector t? So to begin with, let's remember that the unit tangent vector, capital T, represents the direction in which the object is moving at any given moment. And let's also remember that the derivative represents the change in a quantity over time. So putting those two pieces together, if we think about the meaning of capital T prime must represent the change in the object's direction of movement, which is just another way to think about turning. When you turn, your direction of movement changes, so that's why T prime represents where you're turning at that instant. Now, capital N is just T prime that's been rescaled to turn it into a unit vector. And so because T prime shows you the direction in which your object is turning, N also shows you the direction in which your object is turning. So that's the explanation for that particular property of N. Now let's explain why N is specifically perpendicular to T at any given moment. And in order to explain that and prove it to you, there are a couple of prerequisite results, prerequisite proofs that I will have to give you to talk about some special properties of derivatives and dot products for vector valued functions that we haven't talked about yet up to this point. And the first thing that I need to tell you about is that the dot product satisfies a product rule, the same kind of product rule that we had in Calc 1 for scalar valued functions also applies to vector valued functions and the dot product. If you take the derivative of the function v of t dotted with the function w of t, then that's equivalent to if you take the derivative of the first function and leave the second function alone, and then add that to if you take the derivative of the second function and leave the first function alone. To prove that that dot product property is true, let me start on the left side of this equation and calculate what I would get by taking the derivative of v of t dotted with w of t. Just using the dot product formula, this would be the derivative of v1w1 plus v2, w2. And now that I have written out that dot product using the dot product formula, I can apply the Calc1 rules for scalar valued functions to this expression. And I can take the derivative of v1w1 plus v2w2 using the product rule from Calculus 1 to split, for example, v1w1 into v1 prime w1 plus v1 w1 prime, and then applying that product rule again to the term in the back, giving us v2 prime w2 plus v2 w2 prime. So here I've just applied product rule for scalar valued functions to the result of this dot product. Having now written out and simplified what's on the left side of the equation I'm trying to prove, I'm now going to do the same thing and write out and simplify what I have on the right-hand side of the equation I'm trying to prove. So let me look at v prime dot w plus v dot w prime, and let me write all of that out using the dot product formula and using the formula for derivatives of vector valued functions. So I have the vector v1 prime, v2 prime, dotted with the vector w1, w2, plus the vector v1, v2, dotted with the vector w1 prime, w2 prime. If I then apply the dot product formula to that expression, I get v1 prime w1 plus v2 prime w2 plus v1 w1 prime v2 w2 prime. And so what we can see is that every single term in the first expression appears identically in the second expression. So that is proof that the dot product for vector valued functions obeys the same kind of product rule as scalar valued functions from Calculus 1. The second result that I need to prove to you before I can explain why the normal vector is perpendicular to the tangent vector is another property that relates the dot product of a vector to its length. Specifically, when you dot a vector with itself, the result is equivalent to if you take the length of that vector and then square the vector's length. So to prove that, let me start on the left side of this equation, v dot v, and let me use the formula for a dot product to write out what that would be. Using the formula for the dot product, that would be v1 times v1 plus v2 times v2. So that would be v1 squared plus v2 squared. Meanwhile, if I look at the expression on the other side of the equation I'm trying to prove, if I use the length formula to write out what the length of v would be, that would be the square root of v1 squared plus v2 squared. And if I then square that length, the square and the square root will cancel, and that will leave me with the exact same v1 squared plus v2 squared that I got earlier. So this is proof that if you dot a vector with itself, that's the same thing as its squared length. The third and final result that I need to prove before explaining why the normal vector and the tangent vector are perpendicular is a general property of vector valued functions that if you have a vector valued function v of t and its length at all times is constant and unchanging, then v of t is perpendicular to its derivative. So because we're assuming that v of t has constant length, let's go ahead and denote the length by c. C here for constant. And because the length of v of t is constant, if I then square the length of v, then the squared length will also be equal to a constant, whatever c squared is equal to. Now I'm going to use one of the results we proved earlier, that the squared length of a vector is equivalent to the dot product of that vector with itself. If I put that into the equation, I realize what I'm saying is that v of t dotted with v of t is equal to some constant c squared. And now that I've written that out, let me go ahead and apply the derivative with respect to t to both sides of this equation. Now on the right side of this equation, since I'm taking the derivative of a constant, the result of that is for sure going to be 0. So on the right side we have 0, and on the left side we get to use this product rule for dot products that says that the derivative of two functions dotted together, you can simplify that by taking the derivative of the first function dotted with the second function, plus the first function dotted with the derivative of the second function. So in this case, we get v prime dot v plus v dot v prime, and that on the left side is equal to 0 on the right side. Now let's remember that dot product, unlike cross product, had the property that you can change the order of the vectors in the dot product without changing the result. So I can take this expression on the left and rewrite it so that both terms have the form v prime dot v on the left side. And now I see that I ultimately have two copies of v prime dot v on the left side. So what I see here is I have 2 times v prime dot v equals 0, which means that v prime dot v must equal 0. Now remember that when you dot two vectors together and get a result of 0, that only happens when the two vectors are perpendicular to each other. So by this we have successfully proven that v is perpendicular to v prime in the case that the length of v is constant. So now finally we are equipped to prove that the unit normal vector is perpendicular to the unit tangent vector. Let's remember that the unit tangent vector, capital T, was designed and constructed to have a constant length of specifically 1 unit at all times. Because of that, our prerequisite number 3 result kicks in to say that because T has a constant length, T must be perpendicular to its derivative, T prime. But let's not forget that capital N of T points in exactly the same direction as T prime, because capital N of T is just T prime that's been rescaled. So if T prime is oriented so that it's perpendicular to T, N must also be oriented so that it's perpendicular to T. And that's why the unit normal vector points specifically in a direction that's perpendicular to the direction of motion. So that's where this word normal is coming from when we talk about the unit normal vector. The word normal typically refers to something being perpendicular to something. For example, when we talked about vector projection, we discussed the normal force to a surface or to a plane. The normal force being perpendicular to that surface or perpendicular to that plane. So the word normal in math alludes to something being perpendicular somehow, and that's why this is called the normal vector, because it's perpendicular to the direction in which the object is moving. So that concludes today's lesson, and that also concludes this glitched video. In this video, we talked about the unit tangent vector. It's defined as the velocity vector divided by the object's speed, and we also use that formula to calculate the unit tangent vector to a given graph. We also introduced the unit normal vector, which is defined by the formula t prime divided by its length, but we don't want to use this formula to actually calculate n. We'll learn how to calculate n in the next lesson. In this lesson, we focused on this formula and what it told us about the properties of n, namely that it points in the direction the object is turning, and specifically it is perpendicular to the unit tangent vector at every moment.